So hello everyone again. This is a new lecture series on dual nature of radiation and matter. So in this lecture we will understand the actual phenomena of what happens when the ray of light with some intensity, let's say some frequency, gets attracted towards or get approached towards a conductor, or let's say a plate. What happens if the electrons are being emitted, then some of the phenomena, etc. So let's not go into much detailing and discussions. Let me start this. It's a very beautiful chapter. You will get to know about our Albert Einstein also in this lecture. So let's start the lecture directly. So I am Samir Lavankar. This is lecture 1 part 1 of dual nature of radiation and matter. Let's begin our discussion. Okay, so first of all, a course outline for you, as in what all things you will be knowing or you will get to understand in these lectures. So the first is about the introduction, in which you will understand basically why we are reading this concept, why we are reading this chapter. Then second will be electron emission. Electron emission, as in, as the name suggests, electron will be emitted from something. Let's say a plate of conductor, or let's say a charged plate, or let's say a plate which is being surrounded between two plates which are having some voltage difference. So what are these? There are several experiments being observed by different scientists. We will get to know about those scientists also. Then what is actually happening, what is the electron emission, the things related to it, etc. will be dealt in the second point. The third is the photoelectric effect, which is the best experiment which I need to explain to you in this complete concept. So basically the fundamentals of photoelectric effect, what is photoelectric effect, what is this phenomena, how the things evolved, what were the different factors which were considered for the photoelectric effect to take place, and so on, will be considered or dealt in this chapter, fine, or in this topic. Then fourth is the experimental study of photoelectric effect. Then different experiments were being done. You will get to know that even before the discovery of electrons, the study of electrons were already being studied, and then how the studies were being modified, how the things were being carried out, what did the scientists say about this, what were the discussions about them, etc. will be explained in this fourth point. Then fifth is the photoelectric effect and wave theory of light. So basically in this we will get to know about the wave theory nature, that is, as you may have learnt or you have studied the lectures of wave optics and ray optics. So in that we understood that light is basically a phenomena which can be understood partly by particle nature and partly by your wave nature. So how is that wave propagation been taking place in these very small particles, or is there a wave actually observed but we cannot see it on naked eye, or is it not even there visible? So we will get to know about this wave theory of light in this concept. Then Einstein's photoelectric equation, the most important part of this chapter is Einstein's photoelectric equation. What is this equation? We will get to know about different concepts such as cutoff potential, what is V naught, there is what is happening when there is a change in the frequency, etc. We will get to know about H, Planck's constant, etc. in these complete concepts. Then finally, what is a photon? I will get to know, I will make it more detailed, as in what is photon, etc. And finally, there is wave nature of matter and Davisson and German experiment. So what is the basis of Davisson and German experiment? Why is this? This can be understood as the final application of your complete dual nature of radiation and matter. So these are all the things which you need to, which I will convey you in the complete lecture series on dual nature of radiation and matter. So let's start our discussion directly. Let's not waste any time. So let's go on with introduction part, that is introduction of your this new chapter. Fine. So please look over carefully. This is a little bit iteration part, because many information about different scientists, how these things are evolved, etc. will be explained. A little bit about the generation of or the discovery of electrons, etc. will be explained. So just please be listening, please listen it carefully, and then we can move on further. Okay. So the Maxwell's equation of electromagnetism. So basically you may have heard about electromagnetic induction chapter. So in this Maxwell's equation, etc. have come into picture. So that concept has only been explained here. So the Maxwell's equation of electromagnetism and Hertz experiments on the generation and detection of electromagnetic waves in 1887. So if you need to evolve much more interest in it, just look over the years of what are being explained, because I will try to explain to you sometime that even before the discovery of electrons, the concept of electrons were already taken into picture. Just they did not know that these are known as electrons, they are negatively charged particles, and so on. Okay. Okay, let's go on. Then so the Maxwell's equation of electromagnetism and Hertz experiments on the generation and detection of electromagnetic waves in 1887 strongly established the wave nature of light. So basically after these things were established, we got to know that this deduced the concept that yes, that light also has a wave nature. So this thing were being introduced because before that Descartes theory etc. were being initialized, and then so everything was being explained using the Descartes theory only, that is a particle theory only, but then different concepts as diffraction, polarization etc. could not be explained using particle theory, and hence different scientists came up, and then they finally till today, in today's date we know that particle nature and wave nature both go in coincidence, that is both go in sequence, and nature of light can be explained due to both of them. Okay. Why sometimes wave nature cannot be explained or why sometimes it can be neglected, we will get to know in subsequent slides, but for now we understood that okay, so Maxwell's equation helped in understanding the or establishing the wave nature of light. Okay. Next, so towards the same period at the end of 19th century, experimental investigations on conduction of electricity, that is electric discharge through gases at low pressures in a discharge tube, led to many historic discoveries. So this was the basic concept of why this new concept or new chapter came into picture, as in because everything was now being analyzed in a discharge tube. Those discharge tubes led to the discovery of new electrons being passing from point A to point B. How were these passing, why was there an electron emission etc. we will get to know, but just this is the basis of how this chapter came into picture, how this concept came into picture. Okay. So towards the same period at the end of 19th century, experimental investigations on conduction of electricity or electric discharge through gases, please remember it was through gases, at low pressures in a discharge tube led to many historic discoveries. Now what were these historic discoveries? So the discovery of X-rays by Roentgen in 1895, as you can see it is at the end of 19th century also, you can see every year is regarding or near the 19th century only. So the discovery of X-rays by Roentgen in 1895 and of electron by J.J. Thomson in 1897. Please remember, it is very important. It is very important discovery as far as our this chapter is considered. Were important milestones in understanding the atomic structure. Fine. So we got to know about the X-rays, we got to know about electrons, etc. Now it was found that at sufficiently low pressure about 0.001 mm of mercury column. So this, so you know that pressure can also be measured in terms of height of the mercury column. So at very low pressure here corresponds to 0.001 mm of mercury column, a discharge took place. So a new thing was being observed, a new when people were experimenting, when scientists were experimenting, they found a new thing. They found that a discharge took place between the two electrodes on applying the electric field to the gas in the discharge tube. So what were these things? So now these is only the analysis which we will get to know. So basically what was happening, let us suppose this is a discharge tube being explained, and then there was a discharge taking place, or there was an emission of electrons from let us say point A to point B. If I tell you in easy terms what was actually happening in this experiment, but for they didn't know that these are something called as electrons, they don't know that there is something there will be some emission, it is everything new to them. So it was one of the important discovery at that time at the end of 19th century. Fine then. So it was found at sufficiently low pressure about 0.001 mm of mercury column, a discharge took place between the two electrodes on applying the electric field to the gas in the discharge tube. So please remember, the electric field was applied, electric field was present at the moment when the electric discharge took place. Okay. A fluorescent glow appeared on the glass opposite to cathode. The color of the glow of the glass depended on the type of glass. So basically different experiments were input, and then it was found that as the glass changes, the color of the fluorescent or the immersion also changes. It being yellowish green for soda glass. So this is just the theory part, you don't need to remember anything here. So the cause of this fluorescence, please remember now, the cause of this fluorescence was attributed to the radiation, okay, which appeared to be coming from the cathode. So basically due to this emission of electrons, which we will get to know, but I am just telling you now, due to that emission of electrons there was a fluorescence, and this fluorescence or this complete process was called a radiation, that is something is radiated from point A to point B. Fine. And it was observed that this radiation is coming from where? It is coming from cathode. Okay. Now these cathode rays were discovered in 1870 by William Crookes, who later in 1879 suggested that these rays consisted of streams of fast moving negatively charged particles. Fine. So even at the moment when they got to know that there was an electric discharge taking place, they didn't know that what was being passed from point A to point B, or let us say from this plate to this plate. Let us say this is the cathode plate, this is the anode plate. They didn't know that what was being passed from point A to point B, but when further analysis was being done, when further people came into picture, when further discoveries were being accumulated, it was found that even before the experiments of 1897, 1895, in 1870s only this thing were explained that even when these cathode rays are being passed, these consist of a stream of fast moving negatively charged particles. These negatively charged particles then in 1897 after a few years were called as electrons. So, as you can see, even the timelines are very mismatched, but the process of information was at moment is being conceptualized and been explained to you in this complete chapter. Okay. So, that is the conclusion of this introduction for this first slide, that these cathode rays were discovered in 1870 by William Crookes, who later in 1879 suggested that these rays consisted of streams of fast moving negatively charged particles. Okay. Please, you do not need to remember anything from here. This is just for you some insightness of why we are reading this chapter, why was there a need to understand these all concepts, why was there an application, why was there a division and German experiment. That is why I am just explaining you bit by bit. Okay. So, this was a complete experiment. This was a cathode, this is your anode. As you can see, air at a very low pressure. This is something called a discharge tube, and then the electrons were being passed from this point A to point B, and hence electricity was being observed, current was being observed. Okay. So, the British physicist J. Thomson confirmed this hypothesis. Which hypothesis? This hypothesis that the cathode rays consist of streams of fast moving negatively charged particles. Fine. Okay. The next thing is, so this thing has also been explained. Next is, by applying mutually perpendicular electric and magnetic fields across the discharge tube, J. Thomson was the first to determine experimentally the speed and the specific charge, that is charge to mass ratio. This is very important as far as your experimental data is considered. So, when this thing was actually been analyzed, or when it was actually been discovered, the E/m ratio concepts, which you will get to know in the subsequent slides, it was a very major discovery that you got to know the value of E/m, and that too you will get to know in subsequent slide that E/m was always being constant. So, that was a very important discovery which was first being analyzed by J. Thomson. Okay. So, by applying mutually perpendicular electric and magnetic fields across the discharge tube, J. Thomson was the first to determine experimentally the speed and specific charge, that is charge to mass ratio of the cathode ray particles. So, he was the first who calculated the value of E/m ratio. So, E/m is nothing but the charge of the electron particle to the mass. Okay. Let us move on then. Next is, they were found to travel with speeds ranging from about 0.1 to 0.2 times the speed of light. So, that is around, let us say 0.1 into, let us say 3 into 10 to the power 8 meter per second, that is equal to 3 into 10 to the power 7 meter per second. Now, this was the approximate speed of these cathode rays. Okay. The presently accepted value of E/m is 1.76 into 10 to the power 11 coulombs per kg. This I think you can remember because this is a constant value. So, the presently accepted value of E/m is 1.76 into 10 to the power 11 coulombs per kg. Fine. As we already know, E is charge, that is the unit is coulomb, and the mass is SI unit is kg, hence it is coulomb per kg. The unit is coulombs per kg, and therefore, the value of E/m is 1.76 into 10 to the power 11 coulombs per kg. Okay. Now, further, the value of E/m was found to be independent of the nature of the material or metal used as cathode, emitter, or the gas introduced in the discharge tube. So, even if you change the air here, the material here, the metal material here, there was no change in the E/m. So, finally, it was observed that E/m is always constant. Okay. So, this observation suggested the universality of the cathode ray particles. Okay. So, that means that final conclusion was that cathode ray particles are being observed everywhere. It does not depend if the air is changed, it does not depend if the metal is changed, the cathode ray particles are always constant. That means some constant thing which is available everywhere in the surrounding is being emitted from, let us say, cathode plate to the anode plate. What were these particles were being discovered further, I will try to explain. These are just electrons only. So, because electron is electron, the charge is always constant, therefore, the value of E/m is always constant. The mass of electron is also constant, therefore, the value of E/m is always constant. Okay. So, this thing is explained and this thing is also been explained. Let us move on then. Okay. So, introduction. So, around the same time in 1887, so as you can see, I guess these things were being explained around the time of 1870, around 1870 and 1875, Williams Crookes 1879, these concepts were being hypothesized and these were being proved by J. Thomson. So, in the similar time frame only, the same timeline only, in 1887 it was found that the certain metals when irradiated by ultraviolet light, please remember it is the main crux, emitted negatively charged particles having small speeds. Okay. So, what was actually happening is that, let us suppose this is that metal being explained. So, when you try to radiated with ultraviolet light, there were some emission of electrons, there was some emission of negatively charged particles, where further got to know, because in 1875 around it was not being discovered that these negatively charged particles are called as electrons. So, they were called as negatively charged particles only. Later in 1895, when J. Thomson proved that this something is called as electron, then they were proved that the things which being evolved or being emitted after the radiation hit the metal is called as electrons. Hence, the electrons are being emitted out. Okay, so around the same time in 1897, it was found that certain metals, when irradiated by ultraviolet light, emitted negatively charged particles having small speeds. Okay, what were these speeds we will get to know in subsequent slide, but for now you can just please just understand the concept that when you are irradiating it, some sort of electrons are being observed out or being coming out of it. Okay. So, also certain metals when heated to a high temperature were found to emit negatively charged particles. Okay. So, even when the metals were being heated up, then they also emitted negatively charged particles, means there was some processes happening in that metal due to which the electrons or the charges of the electrons are such that they emit or they get imparted from the surface of the metals. What is actually happening we will get to know in photoelectric effect and so on. For now you can just understand the theory part and then we can move on. So, the value of E by m for these particles was found to be same. Please remember, as I already said, it does not depend upon the material of air, metal, air, etc. Hence, the value of E by m is always constant. What is its value? It is 1.76 into 10 to the power 11 coulombs per kg. Okay. So, the value of E by m for these particles was found to be the same as that of cathode ray particles. Fine. Okay. So, even if so, what we got to know, that the value of E by m is same. Why it is same? Because even for the cathode ray experiment, the thing which was evolving was negative electron particles only. E by m was always constant there for those particles, those charged particles, and for these negatively charged particles also the value of E by m is same. Okay. Because the particle is same, that is why. So, these observations thus establish that all these particles, although produced under different conditions, sometimes by passage of electricity, sometimes by passage of ultraviolet light, were identical in nature. J. Thomson in 1897 named these particles as electrons. So, when it was discovered, when he tried to write a name for the complete negatively charged particles, he wrote it as electrons and suggested that they were fundamental universal constituents of matter. Okay, so, these are present everywhere and that is why it does not depend that there may be any air, there may be any metal here, because electrons are electrons only, electrons are negatively charged particles and hence they will have the constant value of E by m. Okay. Let us move on then. So, for the next thing, for this epoch making discovery of electron through his theoretical and experimental investigations on conclusion of electricity by gases, he was awarded a Nobel Prize in Physics in 1906. So, that was one of the conclusion only of this concept. Fine. Now, there was one more experiment in the similar basis which was done by American physicist R. A. Millikan. So, in 1913, the American physicist R. A. Millikan performed the pioneering oil drop experiment. So, this was called as oil drop experiment, as I already explained here, for the precise measurement of the charge of an electron. So, basically for calculating the value of charge precisely, he did the Millikan experiment. So, he found that the charge on an oil drop was always an integral multiple of an elementary charge, that is 1.602 10 to the power minus 19 coulombs. So, this was being calculated. So, Millikan's experiment established that electric charge is quantized as it has a value. From the values of charge E and specific charge E by m, the mass m of the electron could be determined. So, quite evident, as we know the value of E by m, that is equal to 1.76 into 10 to the power 11 coulombs per kg, and we know the value of charge is equal to 1.602 into 10 to the power minus 19 coulombs. Hence, the value of m can be calculated as equal to E by m, right. So, this was the just the calculation part, nothing very similar. You can just remember, please remember, you need to remember at least this, because these are being asked in some of the questions, you need to remember that, and hence this is the conclusion of your complete introduction. So, finally, what we understood in this, I will try to start this in the next part. So, in the introduction part, what we got to understand is, because of these such experiments, when the ultraviolet light were being passed through this cathode rays, or when the cathode ray experiment was being done by J.J. Thomson, etc., there was some particles which were being evolved from, let's say, point A to point B, which were being emitted from point A to point B. What were these particles? It was later discovered that these were electrons only, and one of the conclusion was that E by m is constant. It will be constant because it is surrounded everywhere, and every time electrons are only emitted. And finally, using Millikan's experiment, we got to know the value of charge precisely, which is equal to 1.602 into 10 to the power minus 19 coulombs. Using this value of E by m and E, we can get the value of mass as E divided by E by m. Fine. Okay, so let me end it here only. So thank you so much.